warm welcome to all of you. In the past few lectures, we were discussing about critical state soil mechanics. We have already seen the basics. We have also seen the two-dimensional representation in the last lecture. While discussing the two-dimensional representation, you might have noticed that we discussed about the rightmost boundary for the soil to exist, and that was isotropic consolidation line or normally consolidated line, which forms the right boundary. In the last lecture, we have also seen a tension cutoff zone which appears on the left side, beyond which the soil cannot sustain. And bottom part, we have the axis itself where shear stress is equal to 0, where Q or the deviatoric stress is equal to 0. That forms the bottom boundary. But what is the top boundary? One can conveniently say that it can be a critical state line. You remember there is a line in Q P dash or tau sigma dash plot, and that can be considered as the boundary provided. Why? Because the soil ultimately fails on it. But in fact, for those soils which dilates, we know that it has to first hit the peak and then come back to the critical state line. So, the top portion, if you want to really consider the boundary, it has to be the peak state, because peak state is above the critical state, even though the final failure happens at critical state. So, today's lecture we will see more specifically about peak state, which happens to be another boundary for the soil to exist. And finally, what we are trying to do, we are through critical state framework, we are just trying to understand the bounds within which the soil can be loaded, that is where the soil can actually exist during shearing. So, with this we will now start with what is known as peak state. Now, let us consider two reference void ratios, E1 and E2. Let us say we are considering E sigma dash plot, and the critical state line is marked in this. Since we are considering the peak state, we do not have to really bother about normally consolidation line, because we know that peak state is relevant to over consolidated or dense sand, and which lies on the wet side of the critical state mostly. So, we will discuss about E sigma dash. Now, there are different ways of representation, all majority of them we have already discussed. It can be on log sigma dash plot as well, but here specifically it is on a linear scale. Now, this is the reference void ratio E1 and E2. It is noted, you can note that E2 is less than E1, that means this is a more dense state. Now, shear strength test is conducted at identical E and different confining stress, and that is what we do. If we want to determine the strength of the soil, we need to have at least 3 identical samples, and these identical samples means the initial state has to be comparable for all the 3 states, and that means that the void ratio has to be same, or the water content has to be same, the initial state. And then we choose 3 different confining pressure, whether it is in direct shear test or whether it is in triaxial test. We need to conduct it at 3 different confining stress. That is what is written here, at least 3. So, 3 confining stress. So, this is what at E2, these are the locations at which, or these are the sigma dash at which the shear test is performed, and the last point being on the critical state line. So, let this be PQ, and for E1 the same void ratio, but with different effective stress or the confining stress. So, it can be denoted as RS. So, there is a PQ series and there is an RS series. Now, different peak lines corresponding to E1 and E2. I hope you remember, or rather you can refer back to module 2, wherein we have discussed this particular aspect, where for a peak you can have 3 different points and there will be a peak line, and this peak line, when it is fitted using Coulomb's equation, will give the cohesion and peak friction angle. So, let us try to do the same thing here, tau versus sigma dash. This is the critical state line, and for E2, that is at a smaller void ratio, we get the 4 points here, the last point being on the critical state line. So, the peak line is PQ, which meets the critical state line at point Q. Now, if we extend this, or rather if we fit a more Coulomb or a Coulomb's envelope, we end up with a cohesion value and the inclination will be peak friction angle. Similarly for RS. Now, we can note that void ratio E1 is greater than E2. Obviously, the strength of E1 will be less than PQ, and that is very legibly shown in this particular figure. So, that gives CE1. So, cohesion for void ratio series E1 is CE1 and cohesion for void ratio series E2 is CE2. Peak state lines meet critical state line at S and Q. We have also discussed this aspect. As we go on increasing the effective stress, it reaches a point where the effective stress suppresses all the dilation. At that point, the peak state line becomes same as the critical state line. This aspect we discussed, but now there is a lot more clarity in those discussion. Why? Because when we integrate the explanation with respect to E sigma dash plot, this gets quite comfortable and it is very easy to understand, because we know that as you go on increasing sigma dash, there exists a condition where it will meet the critical state line. When you project that down, that will give Q and S. At this point onwards, the dilation is suppressed due to higher sigma dash. This aspect we have clearly discussed. Now, from this point onwards, it will be on the critical state line. Peak state lines are terminated at P and R at low sigma dash. Now, you can see here that it does not extend beyond this, because it is very difficult to find out or to simulate a condition of low stress lower than this particular point P or R. So, it gets terminated, peak lines are terminated at P and R at low sigma dash. Now, beyond this, it does not follow the Coulomb's equation, tau is equal to C dash plus sigma dash F tan phi dash at low sigma dash. Now, I do not know whether you will be able to really appreciate this particular point or not, because we never bothered about this particular aspect. When we conducted the test, maybe for finding out peak friction angle and cohesion. So, cohesion would exist only if we are dealing in terms of peak friction. So, both goes hand in hand. Now, when we discuss this, or when we have already determined this in the lab, we have got 3 points and we have just fitted. How low stress value we have considered, we have not bothered about it. In fact, the authenticity of the stress points towards the lower end is restricted because of certain factors. One important factor is the tension cutoff zone. and the other one is what we are going to discuss now. So, this particular equation for the time being is more like a mathematical fitting parameters. How sound or how much physically relevant these parameters are. Definitely phi dash has got its own physical significance, but then whether C dash is always justifiable or not, that is what we will just see now. Peak line is equally valid for clays and sands. This also we know, because when we say clays, we talk in terms of over consolidated or normally consolidated, and if it is over consolidated, we say that there will be dilation, there will be peak, and there will be C dash which is associated. And in the case of sand, we say that for dense condition, it will be exhibiting a peak friction angle. But what about the condition close to zero confinement? Can it have cohesion? Definitely not. So, that is the reason, that is another reason why we say that in general the Coulomb's envelope or Coulomb's equation may not be valid for lower stress condition. Sands do not have shear strength at 0 sigma dash, at 0 confinement sands do not have any shear strength. So, in general cohesion C dash cannot be considered as shear strength available at 0 sigma dash. So, we cannot generalize stating that sigma dash is always the shear strength at 0 confinement, because that is not valid for at least sandy kind of soils. So, where it will be applicable? C dash is primarily a mathematical requirement of Coulomb's model, and it is valid for soils with cementation characteristics. Definitely one can always say that those soil which exhibits a kind of cementation characteristics, it can hold on its own even if there is no confinement. So, in those cases, and that can be also due to apparent cohesion, and apparent cohesion may not be available all the time. So, that also we need to be careful about. So, we are basically discussing about in depth the understanding of peak and the cohesion behavior of the soil. Definitely if there is a kind of cementation, it is bound to exhibit cohesion, and for that particular reason we can always extrapolate the results, so that intercept can be considered as cohesion. We have seen that different E1 and E2 will result in different C and phi dash characteristics for peak line. Now, let us try to make it unified by the process of normalization. In the last lecture, we have already seen how to normalize a given plot. So, the normalizing parameter is sigma dash C, that is the stress condition or the confinement which corresponds to the critical state line. So, sigma dash C is the normalizing parameter, and in this case there will be sigma dash C1 and sigma dash C2. So, sigma dash C1 for E1 series and sigma dash C2 for E2 series. This will be the normalizing parameter, and what we will normalize? We will normalize tau and sigma dash. So, the normalized parameters are tau by sigma dash C, sigma dash by sigma dash C. We have done this in the previous lecture, and we have seen that critical state line and normal consolidated line comes to a particular point. The line is represented by a point. How this is so? Please refer back to those lectures. So, this is the normalized plot. Here different peak state lines for different E, it reduces to a single line PL. Do not think that this is a critical state line, this is done with a specific purpose. That is why it is drawn in dashed line. This dashed line is not critical state line. Critical state line is represented by this particular point, and this line is only meant to show the slope. So, PL becomes the peak line which is normalized. Now, the effect of E1 and E2 goes away. Whatever we have got as PQ and RS, it is all it all merges to PL. All the data points will be on this line because of the normalization. We have seen that this is 1 and NCL is a point on the x axis. So, this parameter C dash P is a normalized parameter and phi dash P is the inclination of the normalized plot. Rather, phi dash P will be same as this plot as well, because it is only a division by sigma dash C. So, L is the critical state point where it merges on the critical state line. Now, we can always write the equation of the peak line PL, which is the normalized plot, as tau divided by sigma dash. Now, I have added tau P here just to make sure that it is the point on the peak line PL. So, tau P by sigma dash C is equal to C dash P plus sigma dash P by sigma dash C tan phi dash P, in which C dash P can be written as CE upon sigma dash C. CE is the cohesion corresponding to a given void ratio. So, it can be CE1 or CE2. Now, that will be getting reduced by, or that will be getting factored by sigma dash C. So, CE1 upon sigma 1 dash C or CE2 upon sigma dash C2, whatever. So, that normalized value of cohesion is C dash P, as you can note from this figure. We can also write C dash P is equal to tan phi dash CS minus tan phi dash P. How this is possible? Now, this expression is possible only on the normalized plot. Why? Let us consider tan phi dash CS. This is the triangle inclination tan phi dash CS. So, tan phi dash CS is equal to, let us take this distance as y upon 1, because this is 1. And similarly, if you consider this particular triangle, we can write tan phi dash P. Let us call this as y1 and this will be y2 by 1. So, y1 is equal to tan phi dash CS, y2 is equal to tan phi dash P. So, in short, what we are writing is C dash P is equal to y1 minus y2. That means that is tan phi dash CS minus tan phi dash P. So, substituting this in this particular equation, we can write tau P upon sigma dash C is equal to tan phi dash CS minus tan phi dash P plus the same sigma dash P upon sigma dash C tan phi dash P. So, now the parameters C dash P, that is the normalized parameter, phi dash P, phi dash CS is independent of E or W, which is the initial condition, because now we have normalized it, and hence the effect of E1, E2, or it can be told in terms of water content for a saturated sample, the effect goes away. So, it is normalized now. So, this parameter, it is independent of the initial condition, that is E. Hence, these parameters can be considered as fundamental parameters only after normalization. But there is a catch here. Can it be really considered as a fundamental parameter? Under certain condition. If we consider another parameter, that is the confining stress, then you will see that the things will be different, and this we will explain in the slides to come. For the time being, if we are referring only to the initial state, that is the void ratio or W, we can consider this to be still a fundamental parameter after normalization. Now, let us try to repeat this in VQP dash plot, because this is important. Finally, we will be explaining all these aspects on VQP dash plot. So, I am not going to spend much time, it is the same explanation. We have a reference V for which 4 tests has been conducted, PQ, and the same has been shown on QP dash plot, where MC is the slope and GP is the intercept on Q axis. P dash C corresponds to critical state. Here we can also add the tension cutoff zone with an inclination of 3. Let this slope be HP, which is given as tan phi dash P, where phi dash P is the inclination of PQ line. Equation of line PQ corresponding to a particular V. Please note it is for a specific volume. QP, that is Q on peak line PQ, is equal to GP plus HP into P dash P. P dash P means P dash on the peak line PQ. So, this is the equation and that is very straightforward. And if we normalize using P dash C, which is the point on the critical state line, we get the normalized plot where HP is equal to tan phi dash P, that remains same. GPV is the normalized G parameter with respect to specific volume V. This is 1 again. Equation of normalized peak line can be written. This is normal consolidated line point. QP by P dash C equal to GPV, which is from here, plus HP into P dash P upon P dash C. It is the same exercise as we have done before, and this GPV is equal to GP upon P dash C. GPV can also be written as MC minus HP, where MC is the slope of this line or this particular line, and here this distance, as we have done in the previous case, it will be MC minus HP. So, QP by P dash C from here is MC minus HP plus HP into P dash P upon P dash C. As like before, parameters GPV, that is normalized parameter, MC, HP are fundamental parameters independent of E or W. It is fundamental parameter only because it is not dependent on initial state. It is independent of the state variable E or W. As I told, there is another hidden part here which may violate this fundamental nature, that we will see a bit later. The contribution of E or water gets included in P dash C in this particular parameter. The effect of E and W is inclusive in the normalizing parameter P dash C. That is why it gets normalized. Now, let us see something what is known as power law equation of peak state. Now, we have represented the linear representation of peak line in a normalized parameter. We would also like to see if we actually consider the real behavior, how it would look like. When I say real behavior, what I mean is, we have told that peak line cannot be extended beyond a certain point on the left side or towards the low confinement stress region. So, if that is the case, is there a better model to represent peak state, which is even more general than the linear representation? Granular soils which are not cemented will have 0 strength at 0 effective mean stress. Now, this aspect is not considered in the linear representation for peak state. So, that is very important. So, when we represent the peak state using a linear fitting, it is bound to give an intercept, and this is not valid for soils which do not have cementation characteristics. So, let us see this in detail. It is apparent that the peak line should pass through origin for this particular case, where there is 0 strength, then it has to pass through the origin, where QP is equal to P dash, that QP means Q on the peak line, P dash P, P dash on the peak line, that will be equal to 0. So, it has to move through the origin. We also know that on the right hand side, peak line would also meet critical state line. It cannot go on and on. So, it will meet at critical state line where the dilation gets suppressed and the peak behavior is no more possible, a peak gets suppressed, and that is QC equal to MC P dash C where it meets the critical state line. Now, this could be achieved only using a curved line. If we want to meet this condition and this condition, it has to be a curved line. Now, please understand, we are slightly breaking certain rules which we felt it is actually the case when we studied during our undergraduate. So, as we move forward, we have to add more and more details to what we have already learned, and in the process we may have to break certain rules with which we have understood the shear strength concept, and this is one. The peak behavior is very critical, and which we have not discussed in detail during our undergraduate days. So, this could be achieved using a curved line, because for soils we do not discuss about this curved failure envelope to represent peak behavior. This is very much dealt when we discuss the behavior for rocks, but the same is not considered when we discuss for soils. So, this curved line, a very simple equation can be of that of power law. If we represent the peak state points using a curve like this, which is a power curve, then this will satisfy that it goes through the origin and it meets the critical state line. So, both the points are actually met, and that can be represented as QP is equal to M into P dash B, where M and B are the power equation parameters. In log, we can also write this as log QP is equal to log M plus B log P dash, and that can be represented as a straight line, because then it becomes, on a log it becomes a straight line where there is log M B, and in the normalized plot we can write Q by P dash C, P by P dash C. We can write the power curve in this particular manner, M dash C, and this particular intercept will be equal to MC, because the slope is MC that we have seen. Since this is 1, this distance becomes MC. So, we can write the equation for this curve as QP by P dash C equal to MC P dash P upon P dash C raised to beta. So, the same equation altered in the normalized plot, where MC and beta are soil parameters and depends only on the soil type. Now, let us make a comparison. Now, we have discussed the various nuances associated with peak state, which we have not studied earlier. Now, what is the implication of this? What is the implication of the more generalized representation of peak state using power law curve vis-a-vis what we already know, which is the Mohr-Coulomb failure envelope, or we can also call it as Coulomb's failure envelope, because we are representing in terms of tau and sigma dash. So, how do we make this comparison? Let us see. For this, I am considering two cases of peak shear strength for 3 identical samples in normalized plot. So, now we will consider only normalized plot, because we have discussed in detail about how E and W is going to affect the initial state, how it is going to influence. Now, the other aspect, which is the role of confining stress, that is what we are going to see in this particular slide. Now, for that, what we are doing is we are considering 3 identical samples, the way we use it for shear strength determination, and we are representing it in normalized plot, and there are 2 cases which we need to consider. Now, the first case, case 1 on the normalized plot, This is the power curve, which is the more general representation of the peak state. Let us consider these three identical samples are A, B and C. Now, why this is case 1? In case 1, the three identical samples are close to critical state line, that is towards the critical state line or the rightmost portion of the peak curve. Now, in normal practice what we do, we fit a best fit line and we call it as Mohr Coulomb failure envelope or Coulomb's envelope, and we get the cohesion and the friction angle, that is phi dash P1 because it is case 1. So, the peak friction angle is phi dash P1 and the cohesion given is C dash P1, and 1 represents that it is case 1. The power curve passes through the data, that is best fit, and the critical state point. So, the power curve passes through even origin, through the data and the critical state point. Now, we are best fitting a linear envelope or Mohr Coulomb envelope to the data. So, what we see in case 1, the data points are close to critical state and this is the best fit curve, and we can see that it gives a cohesion and friction. Now, what is case 2? Now, case 2, the data points are towards origin, that is towards this or lower sigma dash. So, this is case 2, same power curve, same identical state, but we have chosen D, E, F, that is the 3 normal stress or effective stress towards left side or towards origin. Now, what we do? We have to again fit the Mohr Coulomb failure envelope. So, this is represented as MC2 envelope and given by the friction angle phi dash P2 and C dash P2. So, this is what we do for peak envelope. Now, we can see, we can compare the power curve which is general in both the cases, case 1 and case 2, whereas MC1 and MC2 there are marked differences between case 1 and 2. So, MC1 and MC2 do not pass through the critical state point and origin. So, for peak we know that it has to pass through origin because to satisfy the lower end, and it has to pass through the critical state to meet the satisfy the upper end. Now, both the Mohr Coulomb failure envelope best fit line will not pass through these 2 points. So, you can see that the Mohr Coulomb is a kind of violation for representing the peak behavior, but still it is valid. We will see how. Now, not passing through origin is not applicable for cohesionless materials and those soils with only apparent cohesion. So, what is the implication of not passing through origin? If it is Mohr Coulomb is not passing through origin, means it is not applicable for a cohesionless situation or for the soil where there is no proper cementation, it cannot hold on its own, because in apparent cohesion we cannot consider it as a true cohesion. So, those soils which cannot sustain on its own, it may not be able to represent the lower stress conditions. This is applicable only for true cementation in soils. Not passing through critical state violates the fact that the soil keeps dilating even at high sigma dash. So, the contribution of suppression by sigma dash is not accounted if the Mohr Coulomb is not passing through the critical state point. So, these are some of the violations which we have to keep in mind when we use Mohr Coulomb failure envelope for representing peak behavior. So, both MC1 and MC2 best fit and it adequately represent the data points. There is nothing wrong in representing this particular line because it adequately represent this particular range of data. It also represent this particular range of data, but what matters, the range of sigma dash considered matters. That is why MC1 is practically different from MC2. The parameters provided by MC1 and MC2 are different. C dash P1 is greater than C dash P2 and phi dash P1 less than phi dash P2. Now, C dash P and phi dash P1 cannot be considered soil parameters if the range of sigma dash is considered. Now, we are just going against what we have told in the previous slide, where these normalized parameters C dash P and phi dash P can be considered as a fundamental parameter, provided we are referring only to the initial state, then it is correct. But if we are considering the range of sigma dash, as you can see here, this is one particular range and this is another particular range. If the range of determination of sigma dash comes into picture, then you can see that both C dash and phi dash peak changes. So, it is dependent on the range of sigma dash for measuring peak strength. So, MC envelope parameters are widely used in practice because we never look at the power curve. What we are interested in is the representation using Coulomb's envelope. All the numerical evaluation, even all the programs that we use, it is all basically based on Mohr-Coulomb failure envelope. So, for uncemented soils, curved power law passing through origin and critical state is more applicable, or it is more general in nature than Mohr-Coulomb failure envelope. Peak strength measured for wide range of sigma dash is close to power curve. Now, if we include different range or during the determination, then that particular Mohr-Coulomb envelope will be a more generalized and close to what we represent using peak. Now, we can see another important aspect. Mohr-Coulomb parameters are unconservative and overestimate the strength for the range of sigma dash, please understand this, beyond which peak strength is determined. Let us take the example here. Now, for these three data points, it fits very well. So, if this is the range considered, nothing wrong, it goes hand in hand with the power curve. But the moment it exceeds the range, that is towards this side and towards this side, we can see that Mohr-Coulomb failure envelope is above the power curve. If this is the actual strength available, the predicted strength based on Mohr-Coulomb towards the lower end is this. Similarly, in the upper end it is this. So, it is an overestimation, and whenever we overestimate strength, it becomes more unconservative. Whether that much strength is available or not, that is a kind of debatable subject, but then according to the mathematical framework, what we need to understand is that the Mohr-Coulomb beyond the range for which the strength is determined. Now, it is same for this also, this is the range. So, beyond this there is an overestimation of strength by Mohr-Coulomb failure envelope. We are basically working with higher strength. For a designer, this is not good. So, for the range for which the sigma dash is determined, if the same confinement is there in the field, then whatever we are telling is correct. So, that is why we have not discussed these aspects in detail during our UG learning. There it is presumed that whatever peak strength values that we are determining, it corresponds to the given confinement in the field. So, sigma dash that we use for strength determination, it adequately represents what is there in the field. Hence, there is no dispute. Otherwise, there are a lot of loopholes when we consider Mohr-Coulomb failure envelope, which we need to keep in mind. At least we should be knowing, and we should appreciate this better. Another aspect which we need to discuss is the stress dilatancy and Mohr-Coulomb envelope. Let us consider 4 peak state points B1, B2, C1, C2. That is E. Corresponding to E1, we have A1, and E2, which is A2, which is the point on the critical state line. Corresponding to sigma dash B, we have B1 and B2, and corresponding to another reference effective stress. Sigma dash C, we have C1 and C2, and BC is the point on the critical state line and CC is the point on the critical state line. The same is shown, all the critical state points are mapped, that is BC, CC, A1 and A2. Now this 4 points represents many different aspects. B1 and C1 same E1, B2, C2 same E2, where E2 is less than E1. Now the points B2 and B1 corresponds to same initial effective stress, that is sigma dash B, but E1 is greater than E2. So this and the overconsolidation ratio will be different for B1 and B2. The amount by which B1 is overconsolidated or B2 is overconsolidated, it differs. So there, this 4 points represents adequately different aspects of stress dilatancy. So let us consider peak, which is represented by B1 C1. Now this has same E1, so this B1 and C1 will lie on the same peak line, and B2 and C2 will lie on the other peak line, and you can see that E1 is greater, hence the strength is lower, and the corresponding cohesion is C dash P1 and C dash P2. Now let us consider there is a given line here which is drawn to show psi dash P. What is psi dash P? You can refer back to module 2, it is the dilation angle which is over and above the critical state angle, and summation of these two gives the peak friction angle. So phi dash P, if this is the peak line, phi dash P is the critical state plus the dilation. Now B1 C1 have same E1 and lie on more Coulomb failure envelope, which gives C dash P1 and phi dash P. We have already seen that. B2 C2 have same E2 and it lie on more Coulomb failure envelope, which gives C dash P2 and phi dash P. B1 B2 have same sigma dash B. Now these 2 points we are referring, it has same initial stress condition, but B2 is more OC than B1. You can see that it goes down and it has to come, so this much allowance is there. So B2 is more OC than B1 and E2 is less than E1. So these are the 2 important conditions. Now if you refer to this, B2 is more OC than B1 means if we draw a line through B2, you can see that the dilation angle is more for B2, which is a good indication that it is more over consolidated. If it is more over consolidated, it is bound to exhibit more dilation towards the lower stress region. So the dilation caused in B2 will definitely be more than B1, and hence the dilation angle is more. And if you draw this line through origin, you can see that psi dash P for B2 is more than psi dash P at B1. And obviously the E2 is less than E1. B1 and B2 would reach CSL at BC, that is already there. Now B2 have to dilate more than B1. Accordingly, B2 dilates more. Now even though the initial stress condition is same, it does not mean that the dilation is going to be same. We also need to consider how much over consolidated the given sample is. Definitely B2 has to dilate more, and hence the dilation angle will be more. So B2 have higher dilation angle psi dash P than B1. Now let us consider B1 and C2, that is B1 and C2. Now this point B1 and C2 has got same over consolidation ratio. Now if you see B1 from here and C2, these are same over consolidation, or the over consolidation ratio at B1 and C2 are same, and that is very clear from here because this particular line passes through B1 and C2 and the dilation angle is psi dash P. So both B1 and C2 has the same dilation angle. Now, this is possible only if the over consolidation for B1 and C2 is same, and that is why we say that the B1 and C2 has same OCR, but it has different E and different sigma dash. Earlier case we discussed for the same sigma dash. Now here we have different E and different sigma dash, but OCR remains same. Now B1 and C2 has same psi dash P, which can be represented by tau by sigma dash is equal to tan phi dash Cs plus psi dash P, because this tau divided by sigma dash, that ratio remains same for both B1 and C2 because the dilation angle psi dash P is same for both. What it indicates is that for peak points, both the stress dilatancy also need to be considered, and it is important to specify E, that is the initial state parameter E, or it can be in terms of W, the over consolidation ratio as we have shown here, dilation psi dash P, tau and sigma dash for analyzing and interpreting the test results related to peak soil behavior. So, interpreting peak is slightly more complex than what we generally do for critical state. So, we need to keep in mind these parameters, not to confuse, but to understand that these parameters also significantly contribute towards the peak characteristics. So, that is why in certain design we see that the cohesion characteristics is ignored. Why? Because we do not know whether it is going to mobilize that much of friction actually in the field. So, the safe way is to nullify cohesion and only consider the frictional characteristics. So, here what it means is that it is not only the over consolidation or a single parameter that need to be considered. While interpreting the peak behavior, we need to take into consideration the state parameters, OCR, this what range of sigma dash we are talking about, and so on. So, let us summarize today's lecture. Peak state or peak line is one of the boundary state for the soil. So, that is where we started off with. NCL forms right boundary, tension cutoff zone on the left, bottom we have the axis, and the top instead of critical state we have the peak line as the boundary. Soil samples with identical E and varying confining stress sigma dash gives a specific peak line with phi dash P and C dash P. Peak state lines are terminated at low sigma dash and does not follow the Mohr Coulomb failure line. We have shown this. C dash cannot be always considered as shear strength available at 0 sigma dash. The normalized parameters tau by sigma dash C and sigma dash by sigma dash C takes away the effect of initial E, and because it is inclusive in sigma dash C. In the normalized plot, parameters C dash P, phi dash P, GPV, MC, HP is considered as fundamental soil parameters provided the range of sigma dash is fixed. These parameters are independent of E, V or W. Every soil state above critical state line in tau sigma dash plot correspond to a specific E and OCR, that is psi dash P. Equation of peak line is derived. A power law curve satisfies the requirement of 0 strength at 0 effective mean stress and meeting the critical state line at high sigma dash, that we have shown, because this is the most adequate representation and the more generalized aspect. The widely used Mohr Coulomb envelope parameters cannot be considered general for uncemented soils. C dash P and phi dash P1 cannot be considered, or rather phi dash P cannot be considered soil parameters if the range of sigma dash is considered. The power law curve is more general than Mohr Coulomb failure envelope for defining peak behavior. So, Mohr Coulomb parameters are unconservative and it overestimates the strength for the range of sigma dash beyond which the peak strength is determined. So long as it remains within the range, it is fine. So, it is important to specify the state parameter E, OCR, the dilation angle, tau and sigma dash for analyzing and interpreting the test results related to peak soil behavior. So, we have discussed a very important aspect of peak behavior, which you will see later in the state boundary surface. So, this information is valid when we consider it there. So, that is all for this lecture. Thank you.